This is a video on line integrals and conservative and non-conservative vector fields. This is part 1, vector calculus concepts and examples. I'm Scott Vaughn, and the topics we'll cover here are conservative and non-conservative vector fields in two-dimensional space, potential functions, the fundamental theorem of line integrals, and path independence in vector fields. So, what is a vector field? A vector field can be 2, 3, or higher dimensional. It can model gravity fields, electric and magnetic fields, fluid flow like ocean currents or airflow. These are fundamental concepts in physics for mathematical models of gravity and electromagnetism and fluid flow. What you have on the screen here are 3 different graphs of vector fields in two-dimensional space, and underneath these are the vector functions that produce these vector fields. So there's just 2 components because they're each of these in two-dimensional space. So we have an x component and a y component. And at every point in the two-dimensional space, I'm graphing a vector that's based on the value at that point x and y. Now, a gradient is a vector. It is made of the partial derivatives of some function and shows the direction of greatest increase in that function. Also, the gradient is perpendicular to all level curves of that given function. So when we find gradients of functions, we can graph the gradient vector at every point in the domain, and that generates a vector field. But not every vector field is the gradient of some function. And that's a central topic for this video. What you see in this first graph here is a two-dimensional vector field that is generated by this function, this vector function. It's an x and y component where everywhere in the field, at grid points within the field, we've graphed a vector that corresponds to the result at that particular x and y point. And if you're noticing now the color indicates the magnitude. All of these vectors are drawn with the same length because it's a convenient way to graph it, but the lighter color actually represents a larger magnitude. You could sort of confirm that that would make sense. As the x and y get bigger, these magnitudes get bigger. So the closer we are to the origin, the closer these values are to 0, and the smaller the vectors would actually be, which is indicated here by this darker blue color. But there is no function that has this as its gradient. So what that's referred to as is the potential function. So there isn't a potential function for this vector field. On the other hand, another vector field, like the one here in the middle, this is another vector field actually generated by these components. The only change was to put a negative there. And actually this vector field is a gradient vector field for this potential function. So if you took the function negative xy, that's a graph in 3-dimensional space, and its domain is values in the xy plane. So this is the xy plane. It's not a graph of this function. It's a graph of the gradient of this function. This is the gradient. I'm taking a derivative with respect to x in the first component, and so I get negative y. I'm taking a derivative with respect to y in the second component, so I get negative x. So this is the gradient for that function, and graphing it everywhere, this is what it looks like. This is another gradient vector field that there is an associated potential function. If you took the derivative of this function with respect to x, this is what you get right here, this first component. And if you took a derivative of this function with respect to y, this is what you get, this second component. And so graphing that gradient is what's shown here. I'm not graphing the function, I'm graphing the gradient vector field for that function. Basically what this is indicating is the direction of greatest increase in this function at all these different points. That's similarly what's happening here. The arrows are pointing in the direction of greatest increase in this function in the domain space. Like in the domain, what is the direction of greatest increase in the function? Also, you could say that this is graphing little vectors that are perpendicular to level curves. Now let's get to the question of what is a conservative vector field. Essentially, it's a vector field that is the gradient vector field of some multivariable function, but that's with some caveats. We'll say if f, big F, is a conservative vector field with components that have continuous derivatives, then there exists a multivariable function little f that the gradient of little f is big F, the vector field. However, conversely, if big F is a vector field defined on an open simply connected domain, and there exists a function little f such that the gradient of little f is the vector field big F, then the vector field big F is conservative. Alright, that's a lot to take in. Basically, I'm going to go through this in the video. That's what this is primarily about, is to try to pull apart all of the significance of this statement. So that's what I'll do. I know that's quite a lot to think through. So why don't we first focus on this idea of an open simply connected domain. What's that? So open regions are regions that don't include their boundary points. So it's a set of all points except for the boundary of that set. And simply connected, really simply, is regions that don't have any holes or aren't disjoint. So this is a simply connected region here. A technical way of saying it is that if you picked any two arbitrary points in the region, you could connect a straight line between them that would remain in that region. That would be true here, right? Take any 2 points, connect them with a line, and that line will remain in the region. But that's not true here. If you pick two arbitrary points, there are plenty of cases where when you connect those points, it'll go right through a portion of the that is not in the region. It'll cross over the hole, right? And that would be true here, and it would be true here. You could, if you picked 1 point in this region and 1 point in that region, connecting them with a straight line would not remain in the region. So these are not simply connected. So we'll have to be careful to identify open simply connected regions as part of identifying a conservative vector field. So let's look at how in the Stewart book, in section 16.3, it's a section on the fundamental theorem of line integrals, and in that section there's a theorem, number 5. It says, if f, a vector field, two-dimensional vector field composed of a component p, in the I component, a function p of 2 variables, in the I component, a function q of 2 variables, in the j component, if it is a conservative vector field where p and q have continuous first-order partial derivatives on some domain D, then throughout you will have that the derivative of the first one with respect to y would equal the derivative of the second one with respect to x, and ultimately, when that happens, that's what implies the existence of some function little f whose gradient is the vector field. This might remind you of something that if you did differential equations, there is a section there in the differential equations course where we analyze what are called exact equations. And you can solve exact equations in DE, in the differential equations class, exactly when you have this condition. Ultimately corresponds to having conservative vector fields. It ultimately corresponds to the existence of some potential function, and that's why you can solve the differential equation if this condition is met. Alright, so what we have here is really just saying that if it's conservative, then this happens. There is a potential function. But theorem 6, same section, Stewart book, says, suppose that you have a vector field that is composed of some function p of x and y in the I component and q of x and y in the j component. Suppose that is a vector field and it is on an open simply connected region D. Suppose that p and q have continuous first-order partial derivatives. So if you did the derivative of each of these p and q, that's still continuous. And furthermore, when the derivative of the first one with respect to y equals the derivative of the second one with respect to x throughout that region D, then the field is conservative. So this is how I stated it on that earlier slide. I said if f is a vector field, arbitrary vector field, defined on an open simply connected domain, and there exists a function f such that the gradient of f is the vector field, then f is conservative. So it's basically this condition of these partials equaling is what implies the existence of that function small f. Basically, you need this open simply connected domain and the existence of the potential function, and then it's conservative. If you've already studied curl later in the book, and this sort of looks kind of familiar, this is related to calculating the curl. It's similar to doing curl, but curl applies to functions in three-dimensional space, and here I'm only limiting to two-dimensional space. But just for a moment, let's say that Theorem 4 in section 16.5 in Stewart, it says if f is a vector field defined on all of three-dimensional space, and therefore they're requiring it to be an open, simply connected domain, and the component functions have continuous partial derivatives. So taking the derivative of all components, you get functions that are continuous, and if you can compute the curl and it's 0 everywhere, then it's conservative. So basically, computing the curl is very much like this checking that the derivative of the first one with respect to y equals the derivative of the second one with respect to x. Is basically the difference of these is 0, and that would be what you would do in all three components in doing the curl. But this is, for the moment, just studying two-dimensional vector fields. So I'll just focus on those. But it's kind of like when you go into three-dimensional space, you check for the curl is 0. If the curl is 0, and all the partial derivatives are continuous, and it's on an open, simply connected domain, then it's conservative. And as an aside, you may run into this term. If the curl is 0, the field is called irrotational. So vector fields that are conservative are irrotational, and I will look for some opportunities to talk more about that, but in the two-dimensional space for now. So this video, I will continue with these three vector fields, analyzing these two-dimensional vector fields and whether or not they are conservative and what is the implications of that. So again, this is the vector field minus y in the x component and x in the y component. And everywhere in this two-dimensional space, I am graphing a vector that results from plugging that point. Take any arbitrary point, plug it in, the x and y, and you get a vector, and you plot that vector at every point in that space. And of course, they have different lengths, and we're using color here to indicate the lengths, and the lighter colors are bigger vectors. So this is a vector field. Vector fields, again, could represent fluid flow, air currents, wind, might represent an electric field or gravity field. So this is just an arbitrary vector field that's given as a first example. And what we could do now, if the question is whether or not it is conservative, if you took a derivative of the first component here with respect to y, of course that's -1. If you took a derivative of the second component with respect to x, that's +1. It's because these are not equal. That implies there is no potential function from which you could get the gradient equal to this vector field. So this is not a conservative vector field. It doesn't have a potential function to generate it. And a consequence of that is if it's a non-conservative vector field, then line integrals through the vector field will be path dependent. So you could start and end at arbitrary points and get different answers with different paths. So here's a picture of that scenario. Imagine I picked an arbitrary point A and some other arbitrary point B, and I imagine some path through the vector field. And if I compute the line integral, what I'm doing there is basically adding up the components of the field vectors that are tangent to the path. So it looks like we'd be adding, we're kind of going along with the flow here, the flow of this vector field through this path C1. That seems to be pretty much all the way, so it looks like it's going to be positive total contribution from all these vectors. If you add up the tangential components of these vectors along this path, you're going to get a positive. Some places it's larger, and some places that component may be smaller, but overall it doesn't look like there's any negatives, and so I would guess a positive value. And, I would guess a negative value for the line integral along path C2 if you followed from A to B. It looks like pretty much everywhere we're kind of going against the flow, and so if you were adding up the tangential components of these vectors along this path, all those tangential components are opposite to the direction of the path if you go from A to B, and so that would be negative. So it certainly looks like you would get different answers with path C1 versus path C2. So that is the sense in which the line integrals are path dependent. Different answers with different paths. This notation indicates a closed integral, a closed path, a line integral that completes from A all the way back to the same starting point A. Imagine if you took A, from A, path C1, and then from B, path C2 back to A. Well, it wouldn't necessarily add up to 0, because each of these two values, even positive or negative, could be different in absolute value. And finally, a property of a non-conservative vector field is that it is rotational. And the sense of rotational we're talking about is if you pick some arbitrary point, the vectors tend to create a kind of torque on that point. It's like, one way to explain it is if you imagine this as being fluid flow and you dropped a stick into this fluid flow, that stick would actually spin. So the sense of being rotational is not due to the fact that these are all obviously rotating around the origin. No, it's actually the fact that there's a kind of shear here. In other words, because the vectors are getting bigger as you move out, that creates a kind of spin. So not only would the stick float around, the origin here, but it would spin. And it's that torque that is at a particular point that we are referring to when we say it's rotational. So moving to example 2, another vector field, just one minor change. This is a graph of the vector field. All the points in this two-dimensional space from -3 to 3 on the horizontal and -3 to 3 on the vertical. Questions that arise are, is it conservative or not, and what are the implications? And so analysis here, what I'll do is start off with taking a derivative of the first component with respect to y, and that's -1, and the derivative of the second component with respect to x, and that's also -1. And so that there indicates that there is a potential function from which this is the gradient vector field derived from that potential function. And because both of these two components, their derivatives, are continuous functions, that means together, point 1 and 2 imply that this is actually a conservative vector field. So we mentioned that there is actually a potential function because these two guys match, they're equal. That potential function is actually negative of x times y. That's what's a scalar, right? That's not a vector, that's a scalar function, something that you would graph in three-dimensional space. Z would be a height based on multiplying the x and y values together and taking a negative. So, negative, all the values are, well, no, some values above, some values below, depending on the signs of x and y. Anyway, this is indicating the direction of increase in that function everywhere in its domain. So this is the gradient graphed everywhere in the domain for this function. If a field is conservative, then line integrals are path independent. So, for example, if you pick some arbitrary point A and some other arbitrary point B in this field and computed line integrals from A to B, but you use different paths, the answer would come out the same. That's what it means by path independent. The answer is independent of the path. Whatever path you pick, the answer will be the same. So if we added up the sum total continuous integration put together, all of the tangential components of these vectors, all the tangential components of these vectors as we follow this path C1. Some of them are positive, some of them are clearly negative, and in the end we get some total, continuous sum, and that's the line integral, the summation of the tangential components. Well, that result will be the same on any path through this vector field. So C1 and C2 produce the same result in the end. Because they produce the same result, that means that closed path line integrals will always be 0 in a conservative vector field. Because, for example, if you followed path C1 in this direction and reached the point B, And if you got the same thing following path C, well, you can go on path C backwards and get the opposite of what you got in C1, and so the whole thing goes to 0. So line integrals along closed loops are always 0 in conservative vector fields as a direct consequence of that path independence. And conservative vector fields are irrotational, so that there isn't any torque on a point, there isn't any rotation at a point in this vector field. It's kind of an interesting idea, right? It's almost like if it was fluid flow, there's no shear in the flow, and you could say that, just judging by these sort of different length and directions of these vectors, if this was, say, a fluid flow, and if you dropped the stick into that fluid flow, the stick would follow this flow, but it wouldn't spin. There's no torque on that stick. It wouldn't rotate itself. It would just follow, it would follow these streamlines, but it wouldn't itself rotate. It doesn't have any spin. So example number 3, this vector field looks very much like the first one. There's the first one. It's this rotation around the origin, minus y in the first component and x in the second component. And all I've done for example 3 is divide this by x squared plus y squared. So I'm actually dividing by the square of the magnitudes of these vectors. So the numerator is the same as example 1, and I'm just dividing by x squared plus y squared in each component, and therefore basically dividing by the square of the magnitude of the vectors in example 1. So let's go through these same questions as to whether or not this is a conservative vector field and what are the implications of that conclusion. So the first thing to check would be, when it is a two-dimensional vector field, you take the derivative of the first component with respect to y, take the derivative of the second component with respect to x, and those equal. Why don't we just confirm that right now? So we have this vector field with component p. The first component is p and the second one q. And to check, the first thing to check whether it's conservative is the derivative of the first part with respect to y. So the derivative of this first component with respect to y, there's a y in the numerator or denominator. That means I'm going to need to do the quotient rule, so I'll take the denominator and square it, and just copy that immediately on top. And then I'll do the derivative of the top with respect to y, and so that's actually negative 1, minus the top, which is negative y. So the derivative of the bottom with respect to y, and the derivative of that denominator in this first component. The derivative of x squared, that's 0, so we just get 2y. So this whole thing will be negative x squared minus y squared plus 2y squared over the quantity x squared plus y squared, all squared. And so now we can combine like terms in the numerator. We have y squared minus x squared, everything divided by x squared plus y squared, all squared. Okay, that's the derivative of the first component with respect to y. Let's do the derivative of the second component, q. That was x over x squared plus y squared. And we need to check what's the derivative of q with respect to x. So again, it'll take the quotient rule. So the derivative of q with respect to x, because there's an x on the top and bottom, quotient rule, we'll take the denominator squared, copy that on top. Now do the derivative of the top with respect to x, that's a 1, minus the top, the derivative of the bottom with respect to x, so now it's 2x plus 0, because the y squared goes to 0 here. So the denominator x squared plus y squared, all squared, and the top, that's x squared plus y squared minus 2x squared. So that means we're going to have y squared minus x squared, everything divided by x squared plus y squared, squared. Okay, so how does this look? Yeah, that's the same thing. The derivative of the second part with respect to x, that's the same thing as the derivative of the first part with respect to y. And this implies the existence of a potential function that its gradient generates this field, f. Okay, so we've seen these two partial derivatives equal, and therefore there is a potential function that generates this vector field. But To confirm that the field is a conservative vector field, we've got one more thing to check. Those derivatives have to be continuous on an open, simply connected domain. Looking at those derivatives, they're going to be undefined at the origin and therefore not continuous at the origin. And so if we can specify regions that don't include the origin, the vector field would be conservative on those regions. Those regions that don't include the origin, we would have a conservative vector field. So we have that there is a potential function, f of xy. It happens to be arctangent of y over x. I can do this in another video where we reconstruct what that function would be, but you could just confirm right now that if you did the derivative of this with respect to x, you get this first component. And if you took the derivative of this with respect to y, you would get this second component. So the gradient of the arctangent of y over x is this vector field. This function, arctangent, is the potential function. Its gradient is here. But this vector field is not conservative on regions that include the origin because the derivatives p with respect to y and q with respect to x aren't continuous on regions that include the origin. But it would be conservative on regions that don't include the origin. Now, on those regions where the vector field is conservative, it would be, line integrals would be path independent. And closed line integrals would be 0 on those regions where the field is conservative. And it would be irrotational in regions where the field is conservative. For example, if I took this little region here just as a portion of the xy plane from not including 0, but some point that some region that doesn't include the origin. So let's box off this little piece right here and pick some two arbitrary points within that region, A and B. Computing a line integral along path C1, it'll give you the same answer as you would along path C2 or any other squiggly path or straight line. Follow a straight line path from A to B or path C1 or C2 or any other path. All of them will give you the exact same answer as long as the region that you capture doesn't include the origin. So that's kind of interesting. So if I created a simply connected open domain that included the origin, I could get 2 points where the line integrals would be different. It would be path dependent. So once again, the closed line integral of the vector field would be 0 where the field is conservative, for example, in this region, or any other region that just didn't include the origin, and it would be irrotational, so there is no rotation. So even though, like, for example, imagine dropping a stick into this fluid flow. Well, the stick's going to obviously move along with the path of that flow, but it isn't going to spin. There isn't any rotation. And in other words, there isn't any kind of shear in the fluid flow. And that's because these vectors actually get smaller as you go out, and so they don't produce any torque don't produce any torque at a point. But of course, if you created a larger region that included the origin, you could find points where there is a torque and there is a rotation at a point. Just for comparison, imagine that I change the region on which I define the vector field to include the origin. Now, picking 2 points A and B, these line integrals from C1, from A to B along path C1, it would be different than the line integral from A to B along path C2. That's not surprising, of course, because of the rotation in the field, but it's interesting comparing that with a region here where they would be, paths C1 and C2 would equal, and completing a circle around from A to B and then back to A would produce 0, but in a situation like this, it wouldn't produce 0. Okay, so then maybe to sum up for this part 1, We'll just go back and look at what do we know now about conservative vector fields. Essentially, it's a vector field that is the gradient vector field of some multivariable function, but that's with some caveats, right? If big F is a conservative vector field with components that have continuous derivatives, then there would exist some multivariable function little f that the gradient of little f is the vector field. And conversely, if the vector field is defined on some open simply connected domain and there exists a function little f whose gradient is the vector field, then that field is conservative. So by way of summary, let's say that given a vector field f defined on some open simply connected domain whose components have continuous partial derivatives, that field big F is conservative if and only if there exists a function little f whose gradient is the vector field big F. So that is, conservative vector fields correspond to vector fields for which there is a potential function, that's the little f, whose gradient is the vector field, but this applies only on open simply connected domains. Line integrals are path independent on conservative vector fields and path dependent on non-conservative vector fields. Line integrals on simple closed curves, that is, curves that begin and end at the same point, don't cross themselves, they're equal to 0 on conservative vector fields and not necessarily 0 on non-conservative vector fields. And conservative vector fields are irrotational while non-conservative vector fields are rotational. Okay, so that's the end of part 1. I think in part 2 what I'll do is I'll go back to this function, this potential function arctangent y over x. This is a picture of that function. And here's its gradient vector field, and I'll analyze some line integrals in this vector field. And what's the significance of those line integrals and the results for different regions and different paths, and how does that correspond to this function? But that's the end of this video. Thank you very much for watching.